Welcome to the Central Analytical Facility of Stellenbosch University, presented by the Biogeochemistry Research Infrastructure Platform, or BioGRIP, Soil and Water Node. My name is Jared Van Rooyen, and in this training video, I will introduce you to the analytical methods used to measure and interpret stable oxygen and hydrogen isotopes in water, and in particular focusing on cavity ring-down spectroscopy, or CRDS. In the past, the measurement of oxygen and hydrogen isotopes was exclusively performed using a dual inlet isotope ratio mass spectrometer, or IRMS, where a sample would be vaporized and introduced into a mass spec unit, where heavy and light isotopes are separated using a curved magnet and measured on a detector. In the 90s, this method was much improved using a continuous flow system on the IRMS, which improved precision, cost, and throughput rates. Yet in the early 2000s, laser spectroscopy methods were introduced and became viable, and the measurement of oxygen isotopes changed significantly. So what is laser absorption spectroscopy? And why is it better? Well, it injects and measures specifically targeted isotopolgues directly, but more on that later. It's also inexpensive and can be deployed in the field, and has multiple manufacturers which are better or worse at doing certain things. These new methods have changed the scope of water isotope research, allowing analytical access to those who could not afford it before, or regions that were too remote to collect data from using IRMS methods. Yet the IRMS still has its place, but if you only need water isotopes and samples are less than 15,000 milligrams per liter TDS, then laser absorption spectroscopy methods are much more superior than IRMS. So how does it work? Well, we inject a small sample of vaporized water into a vacuumed mirrored chamber, where a laser of a set strength and frequency will be projected through the sample array. To understand how the laser is going to behave once in the chamber with the sample, we need a quick recap on the electromagnetic spectrum. From the shortest to the longest wavelength of light, we can only visibly see a small portion of electromagnetic waves. The infrared spectrum represents 50% of all the sun's rays, which our atmosphere protects us from. It is this phenomena of infrared wavelength absorption that LAS systems are based. When the water molecule, or any molecule, is excited by electromagnetic waves, there are 6 basic physical behaviors that can be induced depending on the type of the electromagnetic wave and the structure of the recipient molecule. These behaviors affect the absorption and reflection of the electromagnetic waves in a very predictable way. This allows us to tune a laser to a particular electromagnetic wavelength, frequency, and intensity to selectively excite particular molecules, which in our case is the water molecule. Now, if we know which isotopolgues are the most abundant or rare, we can actively select them through their optical behaviors when excited by a unique laser. These rotational vibrational resonance frequencies allow us to identify different combinations of oxygen and hydrogen isotopes within a given sample. Imagine a water molecule was a series of weights hanging on springs, and the tensile elasticity of each spring was equivalent to the strength of the hydrogen bonds of the water molecule itself. Now, if we excited the molecule with a laser, or pulled on the weight, the rate at which the O and H atoms resonate is determined by the intensity of the laser, or pull, and the strength of the bond itself. Now, different isotopes of O and H have different atomic weights, which affect the strength of the OH bond, as well as how it resonates. Thus, if we keep the laser constant, we should see distinct absorption spectra from isotopolgues due to their difference in resonance. The 3 main vibrational resonance frequencies for the water molecule are symmetrical stretch, symmetrical bending, and asymmetrical stretch. As we adjust the wavelength of the laser, we see a predictable change in the resonance of the water molecule. Some molecules resonate in an ideal part of the spectrum. Water and CO2 are among these. They absorb and resonate at well-spaced wave numbers to allow a detector to measure the absorption of each isotopolgue separately. As molecules get larger, they become more difficult to separate using LAS. Yet H2O is an ideal example to showcase here. So how does LAS work? Well, laser light enters the chamber, interacts with molecules, strikes the detector, and the detector measures the intensity response of the light. The detector response depends on the wavelength of the light, since the wavelength of the light is determined by the energy of its constituent photons. If the photon energy matches the excitation energy of a molecular bond in the path of the beam, the molecule scatters the light so that it does not hit the detector. Measuring the laser intensity before and after the interaction with the gas, we subtract the two and determine the absorption. If we tune the wavelength of the light to excite specific isotopolgues, then we can measure the absorption as a function of wavelength. Here we have a schematic of direct absorption, yet a simplified one, where there's a power detector and a signal detector. We adjust the power detector to change the intensity of the laser that's introduced into the chamber itself. Once this light interacts with the gas, it'll be received by the signal detector, and any refracted light represents bonds that have been excited by the specific wavelength or spectrum of the laser introduced. We can calculate this using Lambert-Beer's law, and the only variable in this equation that is of interest to us is the number of the density of the absorbing molecule, which we will train the laser to try and excite. So identifying isotopolgues using LAS, using a loss gas research instrument, of which we have one of our BioGroup facility, is done using a very specific and patented experimental design. Within the cavity itself, lasers travel back and forth between two concave mirrors, sometimes upwards of 20 kilometers. The sample is injected and the cavity is sealed. These light wavelengths have been tuned to specific isotopolgues, are scattered, and never reach the detector at the end, of which the final mirror only lets a specific amount of light through, and we use this to calculate the absorption spectra of the gas introduced into the chamber itself. So ultimately, how do we identify the isotopolgue using LAS? Well, the laser light has specific wavelength passes through the water vapor, and some of that light is absorbed. The amount of absorption is directly related to the quantity of a particular isotopolgue. For example, H2, 18 oxygen. The IR laser wavelength is then chosen to measure the absorption of the other two isotopes of the water molecule, for example, H2O or HDO, or hydrogen, deuterium, oxygen. So how does this look in practice? This screenshot was taken directly from our LGR instrument in the BioGroup lab. Each water molecule has unique optical absorption. The first and largest being H218O, because the 18O molecule is so much larger than that of the 16O molecule. Then H2O, and finally H-deuterium-O. But why is H-deuterium-O so much shorter? Well, this is because the asymmetrical nature of having one 1H molecule and one 2H molecule changes the absorption coefficient of the water molecule itself. Now that we know how laser absorption spectroscopy works, or more specifically cavity ring-down spectroscopy in LGR instruments, how do we make sure that your sample can be analyzed in our facility? Sample collection and preparation is extremely important. Once a sample has been collected, it has to be isolated from the atmosphere. Otherwise, it can exchange isotopes with the water vapor that's found in the atmosphere. To protect our machine, or your machine, samples should be filtered using a 2.2 filter. Samples with electronic conductivities over 2 millisiemens per centimeter are too salty and will damage the syringe, and must either be distilled in a closed system before to remove these salts, but also not fractionate the isotopes, or put through an RMS system. Here we have one of our junior analysts preparing a sample to be analyzed on the LGR system itself. She's using a 1 milliliter pipette, although she needs 2 milliliters of sample for us to run repeats on the sample vial itself. Preferably, we would have at least 5 mils of sample sent in by a client, just in case that we need to run a sample again. It is critically important that the sample is always isolated from the atmosphere to avoid any further fractionation of the isotopes. So now that the analytical instrument has produced data for us, how can we interpret it? Well, we use LIMS for lasers, a software developed by the International Atomic Energy Agency to help us organize, interrogate, correct, and report our analytical data. Laser absorption spectroscopy, and specifically cavity ring-down spectroscopy, suffer from a couple of effects that need to be corrected for in post-processing of the analytical data. The first being the memory effect. Water is an extremely sticky substance, and isotopic signals can be transferred onto subsequent injections. For this reason, we ignore the first 4 injections of every 9 injection run per sample. The instrument will also drift over time, and we need to retune the laser to ensure that it's exciting the specific isotopolgue that we'd like to measure. Our instrument is also affected by its local environment, and keeping ambient temperatures and pressures constant during analysis helps us keep our analytical results constant. In order to keep our machine in tip-top shape, daily, weekly, and monthly maintenance needs to be performed in the laboratory to ensure that our analysis is always precise, accurate, and consistent. In the second part of the video, we're going to take you through a step-by-step procedure on how we post-process our data produced from the analytical machine itself. Welcome to part 2 of this training video. In this portion of the video, we're going to look into the LIMS for Lasers software and what it can do for us. The LIMS for Lasers software allows the user to create customers. It allows you to import and record and assign sample submissions into specific projects associated to that client. It stores and monitors the global and laboratory standards that are used in your laboratory. It allows you to customize sample analysis templates. It prepares configuration files for LGR and Picaro analytical instruments. And then once the analysis is done on the machine, it corrects analytical results for water volume fluctuations during the run itself, which are normally caused by problems with your syringe. It also normalizes your analysis for instrument drift. It allows you to ignore sample injections for the memory effect, as well as any pressure or density flags that occur during the run. It can record multiple runs and create mean values with uncertainty associated, which can be reported to the client. And then it stores your data in specific projects for this reporting process, and can also be used to create invoices for clients. On top of this, you can use it to track your quality assurance and quality control for your lab on different machines and using different standards. In the final portion of this video, I'd like to give a brief summary of isotope hydrogeochemistry, and more specifically, how stable isotopes fractionate and behave in the meteoric water cycle. Stable isotopes of oxygen and hydrogen can fractionate and change in a multitude of different naturally occurring environments. Isotopes that change in crustal environments or between rock matter are not focused on in this video. Alternatively, this video will focus on the meteoric water cycle and how stable isotopes of oxygen and hydrogen fluctuate within it. The reason that there is a distinct fluctuation between stable isotopes of oxygen and hydrogen is because the differences in vapor pressure of different isotopolgues causes a fractionation factor to occur when water changes between phases, specifically between the liquid phase and the gaseous phase, through evaporation or condensation. In general, we monitor the most commonly occurring isotopes of oxygen and hydrogen, being 1 protium and 2 deuterium, and 16 oxygen and 18 oxygen. When we report these stable isotope fractionations, we compare them to standard mean ocean water, or SMAO, as a delta value, with 0 delta being that of seawater. The isotope fractionation that occurs above the ocean is also controlled by the temperature of the ocean and the relative humidity of the air mass above the ocean. If we were to head towards the poles, the temperature of the ocean decreases significantly, and our fractionation factor changes as well. This becomes larger for both oxygen and hydrogen, as heavier water that contains 18 oxygen or deuterium has a much more significant change in the relative isotope compositions of the water that it is being evaporated from. We therefore expect a systematic change of delta 18O and delta deuterium of the rainwater that precipitates from this vapor between the equator and the poles. This systematic change has been identified and reported on extensively across the world. In this example in Europe, we can see a significant depletion of rainfall produced from GNIP stations reported by the IAEA between more southerly and higher latitude. As we move northward into colder regions, we see an increased depletion of stable isotopes. But there are other phenomena on this map as well. It is not just a latitudinal change, and we can see a corresponding depletion in stable isotopes as we move more inland or we move to higher altitude. These effects on stable isotope fractionation in rainfall create an isoscape that allows us to identify different waters in different regions and track these waters as they move through the meteoric water cycle. If we look at the distribution of delta deuterium worldwide, we can see an overall trend of more depleted values towards the poles and more enriched values towards the equator. What else can we see on this map? We can also see a higher depletion of stable isotope variations as we move inland on continental masses, and also isolated to higher altitude regions across the globe. In 1961, Craig developed what is now known as the global meteoric waterline. This is a theoretical change in fractionation of delta deuterium and delta 18O. The corresponding water vapor pressures of these two isotopic signatures creates a trend in precipitation that we can predict, thus being that the delta deuterium value corresponding to any delta 18 oxygen value is likely to be 8 times that of the oxygen value plus 10. This y-intercept plus 10 is known as deuterium excess, which we'll discuss further in this presentation. So how did Craig arrive at the slope for the global meteoric waterline? Well, when hydrogen and oxygen isotopes evaporate from a source, there is a difference in the fractionation factor between deuterium and 18 oxygen. In this equation, we can see that deuterium is preferentially evaporated over oxygen 18 with a larger fractionation factor. In fact, this preferential uptake is almost 8 times more for deuterium than it is for oxygen. Thus, for every 18O molecule that is evaporated into the source, there are 8 deuterium molecules that are evaporated. But the intercept for this line is plus 10. Why? Well, this deuterium excess is a result of the relative humidity above the evaporation source, as well as the temperature of the source itself. This gives us an indication of the climate and has also been used to reconstruct past climates from historical stable isotope records and ice cores. Here we see the global meteoric waterline presented on a delta plot with deuterium on the y-axis and 18 oxygen on the x-axis. Any evaporation that occurs should have a theoretical abundance of 18O and deuterium with a y-intercept of plus 10. As we saw earlier, in low latitude areas closer to the equator, we see a less significant fractionation due to the temperature of the ocean, and corresponding towards the poles or in high latitude areas, we see a more significant fractionation. Along the line, samples that plot more towards the upper right-hand side or closer to zero are likely from lower latitude areas or in warmer climate, and thus corresponding in higher latitude areas that are cooler, we see a more extensive fractionation of the stable isotopes of deuterium and 18O. It is also important to note that extremely heavy precipitation is likely to have a more enriched signal. Although the global meteoric waterline is presented as 8 times 18O plus 10, variations occur across the world, and this is because of their latitudinal positions, their climates, and the continental and altitude effects. Here we can see that northern hemisphere continental areas have a slightly steeper slope and a slightly higher deuterium excess. Here in Cape Town, we have a slightly less steep slope with still a corresponding increase in deuterium excess. This is likely because we're at a lower latitude and receive our ocean from a cooler ocean in the Atlantic. These subtle variations in local meteoric waterlines at different locations help us identify waters in a different region and indicate that global isotope variations are not simply just a function of temperature. There's other things controlling this fractionation. In particular, extremely negative 18O and delta values found at the north and south poles indicate other processes are occurring. These kinetic limitations on the liquid vapor phase mean that equilibrium is not necessarily attained or maintained. Progressive distillation or fractionation of water in cloud masses can also affect the stable isotope delta values of local precipitation. Here enters the concept of Rayleigh fractionation or distillation.
In this sense, in a closed system, the products are immediately removed or isolated from the system. This leads to the starting material that is contributing the vapor to become more enriched or depleted in the heavy isotope. Imagine you had a lake, and the lake began at a delta value of 0. As you evaporated isotopes, preferentially the lighter ones, yes, the cloud mass that is produced is going to have a depleted signature, but what happens to the lake? Well, the lake will become slightly more enriched, and thus the next evaporation event would be more enriched than the first evaporation event. If we evaporate water from the ocean, which has such an extremely large mass, its delta value is likely to not change. Rayleigh fractionation does not explain what we see in the cloud masses. But once the first rains occur and the heavier isotopes are preferentially rained out, so we see a corresponding depletion in the heavy isotope signature in the cloud mass as it moves more inland. Thus, the second rainfall has a more depleted stable isotope signature, and so on and so forth as a large cloud mass moves over a continental landmass and rains out its heavier isotopes preferentially. The positives of the Rayleigh fractionation model is that it can explain or approximately explain the origin of the meteoric waterline near ocean water, the slope of this meteoric waterline, the large depletions of deuterium and oxygen observed in meteoric precipitation in colder regions, the temperature dependence of these two isotopes in standard meteoric precipitation, the high global average of delta deuterium and delta oxygen values in meteoric precipitation, and the correlation between deuterium and oxygen with the amount of precipitation, particularly the existence of large amounts of isotopically heavy precipitation in the tropics and comparatively small amounts of high depleted precipitation near the poles. But what Rayleigh fractionation cannot explain are phenomena that occur outside the concepts of simple stable isotope fractionation as a temperature effect, or stable isotope fractionation occurring in an open system where isotopic characteristics and signatures can change outside the concept of just simple evaporation or distillation. This has consequences for the deuterium excess, as waters change in systems outside of a 25-degree consistent temperature, or climates. And as we know, the world is filled with many different climates. If we look at the detailed global average of deuterium and 18 oxygen for precipitation, the average is around -26 for deuterium and -4.5 for oxygen. Well, this doesn't fit our global meteoric waterline. Why? Well, as we said, this is because we have many different climates, different sizes of continents that occur with different altitudes, and they're not all in the same places in their latitudinal consistence. As clouds move across the world, they also mix with one another. Their water isotope signatures change, not just as a result of further evaporation or condensation. Water in clouds can also freeze, and these supercooling events don't necessarily fit the Rayleigh fractionation model. We can see this in some examples, with stable isotope ice escapes over summer and winter on continents don't behave as expected in a Rayleigh fractionation closed system. Here we have two maps of Africa, the left being in January and the right being in June, showing delta 18O ice escapes developed by the IAEA through a number of GNIP stations. In the north, in January, winter rainfall, especially in the Mediterranean, shows depleted signatures when compared to their summer rainfall. And then in the south, during January, in the summer, we also see depleted values when compared to the winter in the south over Africa. Why is this? Much of sub-Saharan Africa receives all of their rainfall in the summer. And although these large rainfall events should show more depleted values in the winter, they do not. They show more depleted values in the summer. And this is because of the volume effect, as well as the relative humidity above the ocean at the water source. If we look at the stable isotope signatures of precipitation over the world's largest continental landmass, we can see the same stable isotope variations as we move poleward, a decrease in the stable isotope signature, and close to the equator, in warmer, more humid areas, an increase in stable isotope signatures, sometimes even as close to seawater as can be seen anywhere in the world. We also see a corresponding decrease in stable isotope variations over the Himalayas in these high altitude regions. But this cannot explain everything. And if we look in the central part of Mongolia, we see an increase in stable isotope signatures. This is because this part of Mongolia is extremely arid and not a lot of rainfall falls here. These small rainfall events have enriched signals when compared to the rest of the continent. This cannot be explained by Rayleigh fractionation, as simply a function of such limited amounts of rainfall falling in the region. If cloud masses reach this area, heavier isotopes rain out, rather than the large rainfall events seen across the rest of the more humid continent. If we now look in June, in their summer season, the same isotope distribution is not seen, Although a general trend of more depleted values towards the poles is seen, the change in the amount of rainfall received over the continent means that heavier isotope signatures are seen across the entire continental landmass, as was seen in Mongolia in the previous slide. Both the slope and the y-intercept vary depending on a variety of factors. These are generally summarized as the temperature effect, which is controlled by Rayleigh fractionation, the amount of rain, which is somewhat controlled by Rayleigh fractionation but can change in larger or smaller systems, the continental or rainout effect. As you move inland, more depleted signatures are seen, and then the altitudinal effect, where the vapor pressure changes as a cloud is forced into higher altitude from continental landmass, decreasing the fractionation, or the fraction of the cloud remaining, and thus a more depleted signature. So let's look more specifically at the influence of temperature. If we look at these seasonal fracturations, in the warmest months, which are the middle of the year, we can see a corresponding increase in the stable isotope signature with the average temperature. There are a number of physical processes involved in the hydrological cycle which may cause deuterium and 18O values to change and move up and down the meteoric borderline. These phenomena are summarized on this graph, and these are reasons why stable isotope signatures may move off the meteoric borderline, with fluid rock interactions only affecting the 18O values, hydrogen exchange only affecting the deuterium values, and then corresponding hydration or evaporation affecting both hydrogen and deuterium, or deuterium and 18O. Finally, how do you take these theoretical changes in delta isotope values and apply them to your research? Well, on this delta plot is summarized where you'd expect the difference in stable isotope values to occur and how they're going to behave. Generally in winter, you're going to see more depleted values on the global meteoric borderline. Thus, samples should plot in the lower left-hand corner of the delta plot, and corresponding in the summer in the upper right-hand corner. If your vapor source is more arid, you should see a slight movement towards the left of the meteoric borderline, and in humid vapor sources, a slight movement towards the right. Should your water plot in the lower left corner, it could either be a cooler region of higher latitude, higher altitude, or inland, and corresponding, if it's towards the upper right, it's either in a warmer area, a lower latitude, a lower altitude, or it's coastal, thus being closer to seawater. Should you have any secondary evaporative loss from your water source, you'll see your isotope values plot to the right-hand side of the meteoric waterline with a less steep slope. More humid areas will have a less significant change from your meteoric waterline, and more arid areas would have a more aggressive change in the steepness of the slope. Let's see this in examples. If we look at this delta plot taken from several different studies, we can see a significant difference between the Amazon River, the Rio Grande River, and then a river in Darling. Here, the Amazon River stays close to the meteoric waterline, and thus is because of the relative humidity of the Amazon forest itself, there is a significant evaporation occurring from the river water mass. Whereas the Rio Grande occurs in a more arid area, so we see a more aggressive change in slope from the meteoric waterline. This is corresponding in Darling, where we have a similar slope to the Rio Grande, but a much more enriched signal. This is likely because it's a coastal area, and the rainfall in the region is being evaporated and rained out near its source, being the Atlantic Ocean. I hope that this short summary of the behavior of stable water isotopes in the meteoric water cycle will help you interpret your data once it's analyzed in our unit. Should you want to have any more information, please don't hesitate to contact us and ask questions about the use of stable isotopes in hydrological studies. Thank you for joining us for this tutorial on water isotope analysis presented by the BioGrip Soil and Water Node and the Central Analytical Facility at Stellenbosch University.